Thanks. Well, hello everybody. I will speak about fractions. A fraction is a notion that is treated in school extensively, so we should all know what it means. I claim we don't. So here is my account on fractions. The issue. What is the issue? If you would make a survey of books and texts on elementary arithmetic, and you find definitions of fractions, or the concept of a fraction, you will find that there are many different definitions. Most of these definitions, close these doors, most of these definitions are somewhat informal, don't qualify as mathematical definitions, and so on. And in fact, there is no majority. It's all similar. It's all similar in its informality. And I've come to the idea that there are two extremes. The one extreme is that you say that a fraction is a number, say a rational number. That's what I call fraction essentialism. You see the fraction as essentially a number. Number is a mathematical notion, and fraction then also is a mathematical notion, because a fraction is a number. Opposed to this, there is fraction co-essentialism, complementary. And then you say that a fraction is a fractional expression. It's something which denotes a number rather than it is a number. So for instance, if we consider the word car, well, car has 3 letters, but no car as a car has 3 letters. Car as an expression has letters. The car as an entity, the meaning of the expression, has no letters at all, no characters at all. So fraction co-essentialism turns a fraction into a structured entity with at least a numerator and a denominator, whereas fraction essentialism does not at all introduce this structure. In fact, there are many views in between, special kinds of fractional expressions, types of numbers, and so on. There is no shortage of intermediate views between these two extremes. Now, my talk is about how to go about the concept of fraction under the assumption that it's somehow ambiguous between these two extremes. Well, I will introduce the notion of landmarking. Landmarking is the following idea. Suppose you have a notion which you find not sufficiently clear-cut, like in this case fraction. Then you may introduce other notions which are nearby and which have a relatively clear meaning. So you could imagine that you say fraction 1, fraction 2, fraction 3. These are 3 clearer notions which may be helpful in order to define what a fraction is, if you are at all going to define what a fraction is. Now, landmarking is about the introduction of landmarks, and landmarks are notions, as said, which are relatively clear in comparison to the notion that you are thinking about. The first landmark notion is fracterm. A fracterm is an expression with division as its leading function symbol, also called a fractional expression. It's a term or expression of the form x divided by y. And x and y themselves are expressions. Now, so fraction co-essentialism just claims that every fraction is a frac term, and there's nothing else to fraction than frac terms. The other landmark is a frac value, the value of a frac term. Well, frac values are usually called numbers, or in elementary arithmetic, frac values are rational numbers. Then frac sign, this is the notation for a frac term as an abstract thing. So you could, for instance, have 7 instances of the same frac sign on a blackboard. These things are occurrences of the frac sign. So the fourth notion is a frac sign occurrence. And then we have this notion of a quotient. This is relational. If we have A and B as numbers or expressions, then the quotient of A and B is the value of the frac term A divided by B. The underlying idea is this: frac terms have values. Frac values are values of frac terms. If you're writing, you write frac signs, but in fact you write occurrences of frac signs. And the value denoted, the frac value, which is the value of a frac sign, is also called the quotient. Now, my first claim is that each of these notions, frac term, frac value, frac sign, and frac sign occurrence, is relatively clear-cut in comparison to fraction. So a frac term is simply not a frac value. A frac value, let's say, is a number, and a number doesn't have a numerator and a denominator. A frac term is a mathematical tuple, and it's much less specified than a sign. A sign involves fonts, things like that. A frac sign occurrence is even more specified. It has a location, you can see it. Now, so my claim is that these 5 notions are relatively clear-cut in comparison to fraction, where fraction is related to these notions, but it's not entirely clear how it is related to these notions. Now, so this was my claim number 1 in the set of claims I have about landmarking. Frac term, frac value, frac sign, and frac sign occurrences each have a relatively clear meaning, are more specified more sharply, and with lesser ambiguity than fraction. Claim 2, if you have a text, then it's often the case that if you see the word fraction, you may replace it by either frac term or frac value or quotient. It's not so often the case that you need frac sign or frac sign occurrence. It might be so. So the ambiguity of fraction may, in many cases, be dealt with, if you want to do so, by replacing it by a better specified landmark, one of these 3, or perhaps one of the 5. 3, in some cases, this ambiguation doesn't work. For instance, if you have the text, consider the fraction 3 divided by 4. Well, then you simply don't know what's meant. Perhaps someone wants to talk about a frac term and has in mind that a fraction is a frac term, or perhaps someone wants to talk about the number, or perhaps anything else. So in this kind of text, it's sort of self-evident that disambiguation is not a very plausible step. So claim 2 suggests that quite often disambiguation is possible. Claim 3 indicates that this is not always the case. We may, when reading a text, be left with residual instances of the word fraction, for which we have no clear strategy of disambiguation, if we would want to do so. Now, already what I've said now has consequences which would create strong opposition from many mathematicians or mathematical teachers. For instance, 1 over 0 is a frac term for the simple reason that it is an expression. Nobody would deny that 1 over 0 is a fractional expression. So it is a frac term. Whether or not it has a meaning doesn't matter. It being a frac term is entirely independent of it having a meaning. So even if there is no frac value denoted by 1 over 0, 1 over 0 qualifies as a frac term. Secondly, once you know that 1 over 0 is a frac term, the question about its meaning now can be posed and matters. So by talking about frac terms, 1 over 0 is introduced, not by an act of will, but you need an act of will not to view it as syntax, and that will be quite artificial. Like the statement about the Russell paradox cannot as a statement be eliminated because it is a paradox. Russell is entitled to write down a paradox, and then we say that there's something problematic. 1 over 0 as an expression is just not at all infected by its meaning being hard to assess. Now, further, by speaking of frac terms, no position is taken about the meaning of 1 over 0 or other frac terms with a vanishing denominator. All options are left open, including the option without meaning. So that a frac term has no meaning is completely conceivable, and it's no problem at all, but that doesn't mean it's no frac term. Now, frac terms allow a traditional classification. We can talk about open frac terms, closed frac terms, simple frac terms, simplified frac terms, unit frac terms, proper ones, composite ones. Often one talks about, say, simple fractions. If you say simple fraction, then in fact, fraction is understood as frac term. Otherwise, simple would mean nothing. And simplified, the simplified fraction, if you talk about the simplified fraction, then you are clearly not talking about the simplified number. Automatically, you cast frac term as an expression. If we have this language in terms of frac terms, however, it's completely clear-cut. All of what I'm saying, writing here, like simplified frac terms, is comprehensible without any casting or without any resolution of ambiguity. Now, every frac term has a unique numerator and denominator, and these together determine the frac term. So a frac term, in fact, is a pair. Flat frac terms are frac terms for which both the numerator and the denominator do not involve any further frac terms. So the main consequence of introducing frac term is that we have a fairly clear language to speak about these expressions. And in this language, there's just no doubt that things like 1 over 0, 2 over 0, x over 0, x plus 7 over 0 are frac terms, whether or not they have a meaning. We have a terminology usable for the classification of frac terms, like open, closed, simple, simplified, unit, proper, and composite, as it is usually done for fractions. And we know that a frac term is an entity with structure, numerator, denominator, and of course an operator symbol. But in the word frac, it's already clear that this operator symbol is a symbol for division. And we have a notion of simplicity, another notion of simplicity for frac terms, namely not being compositional, and that's flatness. So flat frac terms are non-compositional frac terms. Numerator and denominator are written without division. I would say that all of this is clear terminology, not by itself in need for much further clarification. Now we want to improve our approximation of the meaning of fraction. And I introduce yet another landmarking notion. And this is fraction with an x. I will just say fraction with an x because I don't think that I can pronounce fraction in such a way that you hear the difference, but that doesn't matter. So a fraction is either a frac value or a frac term or a frac sign or a frac sign occurrence. So this is kind of, these things occur in philosophy, disjunctive notions. Is an A or a B. Disjunctive, complementary to disjunctive notions, you have conjunctive notions. All of these, both disjunctive notions and conjunctive notions, produce complications in philosophy. I'm not going into that, but these complications are huge. And here we see that, take the number 7. Well, it is a frac value, but it's not a frac term. 7 may be the value of a frac term, say 14/2, but 7 is not a frac term. 7 may be a frac sign, and an occurrence of 7. No, 7 is not a frac sign, of course not. It's not an occurrence of 7 is not a frac sign occurrence. So 7 is a fraction with an x because it is a frac value, not any other reason. 7/2 is a frac term. Is it also a frac value? Well, that depends on your view on the meaning of frac terms, and so on. In some cases, frac terms will also qualify as values, but you need not look at it that way. These things are tricky. Anyhow, fraction is with an x is a notion which is somehow a mathematical notion, and it incorporates the ambiguity of fraction with CT, the classical notion of fraction, but it does so without being explicit about the strategy of disambiguation. So if you speak about fraction with an x, yes, you still have to find out which of these 4 things are meant. But so I claim that fraction with an x can be used as a landmarking notion, and it gets closer to the classical notion of a fraction, though it isn't the same. Now, having this at hand, we can once more look at the disambiguation of texts involving the word fraction. Well, if the context clearly indicates that either frac term, frac value, frac sign, or frac sign occurrence is meant, then we can disambiguate by replacing an occurrence of fraction by one of these 4. And there may be residual cases. Well, in that case, we replace it by fraction with an x. Still, it might be possible that we get further. But in this case, we know that fraction with an x is only used in cases where we have no clue whether further disambiguation into either frac term or frac value or frac sign occurrence is possible. Typically, this consider the fraction 3 over 4. That would now become consider the fraction with an x 3 over 4. For the simple reason that consider the fraction 3 over 4 as it is written below at the last line of the screen. You have no clue what's meant. A fraction, a frac term, a frac value, a frac sign, or a frac sign occurrence. It could be each of these. So in some cases, this ambiguation is brings you no further than fraction with an x. Then it may be the case that this ambiguation fails. So suppose you have the following sequence of statements. As one says, consider the fraction 4 over 6, and as 2 says, the latter fraction is a number which has an even denominator. Now, whatever you do about it, here you have S1 and S2 together suggest that 4 over 6 is a number and it has an even denominator. Well, this just doesn't go together. If you would write frac term for fraction, then clearly it's not a number. And if you write frac value, then it has no denominator. Now you might say that it's first simplified to 2 over 3, and 3 is the denominator, but then 3 is not even. So there is always a difficulty with this thing. This ambiguation of these two sentences is impossible with the strategy that I just outlined. There's no problem. If this ambiguation using the strategy outlined on the previous page fails, then, well, there's just something wrong with this text. We'll say that the text is not legal. A legal text is a text which, in hindsight or at second inspection, does not allow a workable interpretation, for instance, for the word fraction. Well, legality of texts turns out to be a complicated subject, and one might think from my talk that legality is an issue that comes into existence by being pedantic about the meaning of fraction, but that's not the case. Even the most traditional way of talking about division by zero and insisting that division by zero is avoided leads to fairly complicated considerations about legality. And the imperative that you don't divide by zero in a text, well, leads to a criterion that is not even decidable. So it's not at all clear how to do this in complicated practice. And even if you are not worried by decidability, it's still quite difficult. Well, now I want to move forward to this notion of cross-cutting. If we look at the fraction with an x, then we see that frac value is the most abstract of the four. So if we have a frac sign occurrence, it may denote a frac sign. A frac sign may denote a frac term. A frac term may denote a frac value. You can also see this as a hierarchy of abstraction, where the value is the most abstract understanding of these things. So we have 4 levels of abstraction which somehow coexist. I think there are very few people think about frac terms without having in mind that these things may have values and that they may have occurrences on a blackboard, and that these occurrences are instances of certain signs which then have to be interpreted as terms and then have to be evaluated as values. So in some in some psychological way, if you have one of these notions in mind, you have all of them in mind. Now, the idea is this, that fraction is a concept which I see as a kind of mental picture, an intuition which arises from the totality of these four abstraction levels. So you have in mind a frac term, a frac value, rational number, a frac sign occurrence, and then somehow you think that's all of this is somehow connected. It is about the same thing, but in different ways, at different levels of abstraction. And this intuition, that's a fraction. So fraction as a notion cuts across boundaries between abstraction levels. So we have these abstraction levels represented by the different landmarks, and cross-cutting through these abstraction levels, you have fraction. Now, and at the same time, you conclude that this cross-cutting notion escapes being given a mathematically precise definition. The whole point of this cross-cutting notion is that this cross-cutting is done in your mind, but it's not formally done on paper as a piece of mathematics. Now, hey, what is this? Well, I get no further. Just leave it. Anyhow, let me just finish this talk without being bothered with a small technical failure of this presentation. It doesn't matter. There are several conclusions that can be drawn from this presentation. First conclusion is that it predicts or explains the lack of a precise definition of fraction in the literature, in the educational literature on elementary arithmetic. In this cross-cutting, so if people try to formalize this cross-cutting notion of a fraction with a mathematical definition, they have to choose for one of these four landmarks, or they introduce their own landmark. It's not the case that there are other conceivable landmarks. When faced with the task to define fraction, people will try to define a landmark which they understand and use that as a definition. And what you see is a distribution of possible definitions without a clear statistics. So I think that's quite important. So if people write, as is done quite often in writing about education, that students must understand fractions and that the understanding of fractions should be improved and so on, it's important to be aware that this is an understanding of a notion which has no clear-cut definition. And whatever definition the local teacher will provide, his colleagues will use something else, most likely. Now, I'm not advocating that we should move towards fraction being redefined as a very clear-cut notion. I think it's much more practical to be aware that fraction is a cross-cutting notion which defeats being given a precise definition and which in many cases can be disambiguated. And if something must be defined, then it's the landmark notions. These can be defined, and these definitions make sense for everybody. Now, I want to say a few things about this landmarking because I refer to this as vertical cross-cutting. It's vertical because you cross a hierarchy of levels of abstraction. There is also horizontal cross-cutting. If you look at real numbers may be, for instance, Dedekind cuts or Cauchy sequences or infinite decimal expansions. These are three comparable abstraction levels. And the intuition of a real number is a cross-cutting notion through these three comparable levels of abstraction. So cross-cutting happens all over the place, but in some cases it's borders between the same level of abstraction but expressed in different ways, whereas in this fraction it is cross-cutting over this hierarchy. The big difference is that if you look at Dedekind cuts, Cauchy sequences or infinite decimal expansions, then there are notions of isomorphism which relate these things. These notions of isomorphism cannot be found in the four abstraction levels for fraction. So this is really different. And in teaching, I would suggest that if it's about numbers, then you are best off choosing a landmark notion for numbers. Say natural numbers are decimal sequences. 575 is a natural number rather than 575 denotes a natural number. And then you have the puzzling question, what is a natural number? I mean, if you explain your student that 0 is the name of the object 0, then you are left with the question, what is this object? You can avoid this if you just say 0 is a natural number. That's okay, no problem with that. Now, so I think I hope to have solved or expressed the idea that we should not expect fraction to have a clear-cut and sharp definition, and that certain landmark notions are helpful here, and that frac term is one of these landmark notions. Thank you.
Got the screen sharing.
Yeah.
Go to questions. Let me do it.
Okay.
Okay, so I think you're
I'm visible.
visible. So let me start off. If you have a frac term with a numerator that is an algebraic expression and a denominator which is an algebraic expression, the cancellation of those expressions might have many values. So does your terminology allow for there to be many frac values associated with a single frac term?
Well, I would say it's not designed for that. So the underlying design is that frac terms have unique frac values. The issue that you are talking about arises if both things contain variables and it's more complicated calculation. And I would say that my terminology is at its best for closed expressions. And with open expressions, you really have to go all the way. And so then of course a rational function would take the value, the role of a frac value. But even then, I would say it's a unique rational function, which is the interpretation of a fractor, of an open fractor. If there are multiple interpretations, that's quite something else. This ambiguity would not be intended.
Does anyone else have questions? You can either speak them into the Zoom or type them on the YouTube chat.
It's so obvious.
I have a question.
Speak up.
Yeah, not a question, but a remark. Frege, the philosopher, German philosopher, said that you have objects and the modes of presentation of such objects. So you have the distinction between the sense and the reference. Fractals and fraction are, in some sense, are modes of presentation of an object, or are just a syntactical term. Also, in other words, there is no semantic in your theory. There's no semantic.
Yeah, you do not need to have a semantics for a
Yeah,
factor.
yes.
I agree that that the terminology of Frege applies here, and that to some
Yes.
extent the fractum is a mode of presentation of a value.
Okay.
Still, as far as I know, Frege doesn't explain what fractions are. It is a he speaks about a part of mathematics which doesn't contain that operation.
Yes.
And it's quite difficult to understand how mathematicians go about it. So the traditional way of viewing this is that A divided by B is a notation for the result of dividing A by B if it exists.
Yes.
And quite paradoxically, if you are doing a proof from contradictory assumptions, then you can always prove that it exists and that it doesn't exist. There is no such thing as this existence. So I conclude that it is deeply unclear what it means that a notation depends on existence.
Okay.
I mean, it seems to me to be a priori clear that the notation has priority to its existence.
Okay.
As if 1/0 would not be a notation if it doesn't exist.
So,
Yeah.
so the names of the objects has priority over the objects in some sense.
Yes, I think that this is critical for. So for instance, if I would be asked, so if I were confronted with a mathematician who doesn't like me, and he says, "So you tell me what's 1 divided by a bicycle," then I have no other option than to say, "Well, you started talking about dividing by bicycles, so you explain me what it means." Yeah. And so if I ask a mathematician what is 1/0, then they may say, "You started talking about 1/0, so you tell me what this means." And so my view on mathematicians is that they take for granted that they always and only have notations for entities they want to talk about.
Yes.
And so the question, what is, cannot occur for the simple reason that you will never write something down without having an opinion on its meaning. But I think that this is certainly in times where computing gets stronger. We are simply faced with notations. Now, in a computer, clearly, the computer, which is faced with a fracterm, still has the task to evaluate it. So it's clearly not that the computer is thinking about the value of the fracterm and now reconstructs the fracterm as a mode of explanation. So I would say that, yes, you are right. I introduce priority of syntax over semantics, but I think not as a logical principle. Yeah, I would say that this is, and if you, so John Tucker and I made big efforts to understand what it means. What does it mean to write a text in such a way that you do not divide by zero? So what criterion is this?
Yeah.
And in the simplest form of arithmetic, it's just undecidable. There's no way that you can write a type checker for that. And even if you are not worried, well, then you might say, okay, but let's only look at simple cases where this is decidable. Then what are the conventions? Well, if I write down, say, x divided by y, nobody will complain. If I write down x divided by 0, everybody will complain. Why that? Now, our answer is here. X divided by 0 has no unproblematic interpretation.
Yeah.
There's no substitution for x, for the variables, where x divided by y, isn't it? So certain expressions are worse than other expressions. And as soon as an expression might have an interpretation, it is sort of acceptable. Now, this gives a clue on which texts are legal and which texts are not. Now, if you start working out these clues, it turns out to be complicated and there are different strategies. Then, if you combine this with proofs by contradiction, you get into the following, that you want the denominator to be non-zero. If you work from a contradiction, you know that you will always able to prove that it's zero, because from the contradiction so now the issue is that the proof that it's non-zero must be shorter than the proof that it's zero. That's the rule of thumb, which does the legality check, and it's all entirely undecidable and complicated and vague, and a very big price to be paid for the unwillingness to use all the free richness of these expressions. Yeah. Right. Any more questions?
Yeah, two questions. Now we have the Transmathematics of James.
I don't know what you are talking about. Silence.
Why bother? I can imagine that you try to map out the problems that occur in current thinking.
Yes, of course. I mean, if the whole world would be writing about transmathematics in James' style, and there would be nothing else than that, then this talk would be sort of
Okay.
unrealistic. Exactly.
And historical reconstruction of what they thought before.
Yeah, so I mean, in another world, there would be another talk, clearly. But we are far removed from that world.
Okay.
They say so.
Clarifies a bit what you're working on for me. And the second question is, you use the notion of sign. There was a lot of work on sign in semiotics. I find this theory rather fake, but anyway, did you look into semiotics of this Saussure?
Well, I tried to look into the various meanings attached to sign and token and various of these words.
Yeah, was there something useful?
Well, it's probably very useful, but I wasn't able to use it. Let's say it like that. So I think that in my hierarchy of four things, the Frank sign occurrence is clearer than the Frank sign. Frank sign is a non-trivial level of abstraction in between of Frank sign and Frank term and Frank sign occurrence. But Yeah, I think that this part of the language could be strengthened. I mean, for some reason, I mean, I try to work on very low-level issues for reasons not known to me. I mean, I find it a mystery that throughout the world, hundreds of thousands of mathematics teachers are not worried about their inability to define a fraction. I mean, I've looked at hundreds and hundreds of these papers. I found no single example of a paper referencing another paper for giving the definition of a fraction. So fraction is something that people, it's sort of almost a moral imperative for a mathematical teacher that they know what a fraction is, even if they don't.
It's interesting what we're talking about. When you're studying calculus, you have derivative is a factor, not a fraction.
Yeah,
So there is no difference for a user teacher of math. Don't talk nothing about that.
yeah,
Here
exactly.
you have 4/3. The d phi over dx is the same thing.
Yeah.
For
And
all of
it's
that.
not.
It is not.
No. No, so where does this leave me with your question?
My question about semiotics.
Yeah, semiotics. So anyhow, it's clearly what I'm doing might be naive from certain perspectives, there's no doubt. But I don't, yeah. I think for mathematics, it's the frac term versus frac value which matters. The frac sign and frac sign occurrence, that's much more a matter of natural language. So if I talk about this glass, then of course the glass as a word is not the glass as a thing. So the step from frac sign, from frac value to frac sign occurrence to frac sign is in fact a step that you make in natural language for many nouns. And it's the primary ambiguity from a mathematical perspective is from frac sign to frac term to frac sign.
Vertically speaking,
Yeah.
on a different level.
But I think in many texts you have references to frac sign occurrences. The frac sign, well, if you have the fraction on the last line, it's a reference to a frac sign occurrence. But you never have named frac sign. So let P be the following frac term. That's a text that it's clearly not ever found in mathematical teaching. Right. Thanks a lot. That ends the meeting, more or less in time.
Yeah, you've done well.
Okay. Yeah, welcome everybody. It's a pleasure to give a short presentation on future perspectives of accusation theory. Perhaps you are a bit surprised about the concept, but I will explain it in a minute. And that's what I will do. So I will say something about accusation theory, how the concept was developed. I will say something about papers we have written about it. I will talk about a bit about general features of accusations. And then I will discuss a variety of examples. From there, I will go to some general considerations and talk about future possibilities in which we may develop this concept further. So, accusation theory. The concept was developed by Jan Bergstra and me. And just to be clear about it, I'm not a mathematician, I'm a philosopher with a focus on ethics and political philosophy. And Jan Bergstra is the guy from mathematics and informatics. So we together developed these concepts. The development was quite, there were some occasions for thinking about accusations. We were confronted with accusations in the context of labor conflicts. And we saw in 2020 what happened around the election in the United States. And what we saw was that accusations have a specific function which had not so much to do with the content of the accusation, but with the way accusations are functioning in a social context. So if you remember the election in the US, you remember there were accusations about the stolen election. These accusations were repeated over and over again without any willingness to show evidence for the correctness of these accusations. It was even possible at that time that Donald Trump formulated these accusations before they would actually take place. So already in summer 2019, he said the elections would be stolen. And it seems that the function of these accusations took place without any possibilities of dealing with them appropriately. What we found out is accusations are a very important phenomenon, something which is present all over the world and in everyday life. And only a few accusations end up in the courtroom. So accusations are not primarily a legal phenomenon, but something which is happening in everyday life. If you think a bit about this type of accusation, where the election 2020 is just an example about, you will easily find historical parallels. For example, accusations that certain person are witches. Or think about the McCarthy area in the United States, where everybody was presumed to be a communist. Or think about the Stasi in Eastern Germany, how they dealt with accusations. If we see the importance of these phenomenon, you can be surprised that there is not very much general research. You find some research about wrong accusations in the context of the law. But if you speak about wrong accusations, you know already whether or not an accusation is right or wrong. You find a bit linguistic research, but you don't find research about accusations on a very generic level, so that you just think about what is it, how accusation functions. And in that context, Bergstra came with a proposal to think about accusations in a parallel way as Burgess and Hay thought about promise theory. So that was a starting point of what we did with accusation theory. And I will now show you some examples for accusation. So you find very general accusations. Men are such pigs. Männer sind Schweine. That's a pop band in Germany. All politicians are corrupt. So accusations can be on that very general level. You have accusations like John F. K. was assassinated by the CIA. It's a kind of accusation where the accuser will not be in a position to give any evidence for that. People after a divorce say, you destroyed my entire life. That as well is an accusation of on a very general level. It's very unlikely that it is true in that level of generality. There are these accusations who are made even before something worse happened. You will end up as a criminal if you're grown up. You will throw your grandmother under the bus if you expect to support your career. So that are types of accusations which do not even presuppose that some kind of validation is possible. We have accusations like, he's a horse thief, hang him up, where formulating these accusations and giving a consequence to it are more or less the same speech act, so to speak. And you have accusations like, Hillary Clinton is running a ring of pedophiles in the basement of a pizzeria. That was some 8 or 10 years ago when this so-called Pizzagate happened, where a guy came with a gun to a pizza shop in the village where Hillary Clinton lives, because he had heard in the basement Hillary Clinton was running a ring of pedophiles. I will come to that in a second. So what you see here is the omnipresence of accusations with very different functions. We have these specific accusations. A has murdered B in Central Park on Friday 13, 2020 at 6 p.m. Very specific accusation that could be a starting point of a police investigation. We have general accusations like all politicians are corrupt. We have accusations based on contested facts, like JFK was assassinated by CIA. We have accusations regarding future events. We have accusations as request for actions. We have even accusations not against humans, but as well against God or specific institutions. So he accused God of being unfair to him. And we have these type of accusations who, in that sense, are not meant to be validated, but who are just articulations of a worldview. So if someone is saying Democrats steal elections or Democrats are pedophiles, this person is not thinking, oh, I claim something that's contested and should be validated, but in some circles, people would issue these accusations in the sense of articulating something very self-evident. That means, from their perspective, it's the most normal thing in the world that Democrats steal elections. And in some sense, Trump made use of this, these presuppositions. That was a starting point of a series of papers where Jan and I developed these concepts further. We investigated accusation C in general in the 2021 paper. We had some further development about accusation theory in the context of computer programming. Jan wrote something about promises, threats, and accusations in the 22 Russian-Ukrainian war. We investigated special accusation types like anonymous accusation, non-evidential accusation, and self-accusations. We wrote something about extreme accusations, and from there we came to the genocide accusations in the context of the Gaza situation. I will come back to that in a minute. So that is just to give you an overview about the papers we have written. Most of them are published in Transmathematica. And now to some formal features of accusations. So in accusations, you have an accuser, a human agent, a group of human agents. You have an accusé who is accused, possibly a plurality of accusees. You have an accusation body, that is the content of the accusation. You have a scope containing one or more agents who are made aware of the accusation. And you have a life cycle, which is understood as a speech act. An accusation may be equipped with time and place of being made and may expire at some moment in time. At various stages of the life cycle, an accusation may be repeated, may be modified. Accusees and scope may be modified as well. And so on. So that are the elements which we need to make formal analysis of accusations. And now I go to an example. I want to mention 3 examples in order to show you what we have done with the concept of an accusation. So the first example, so all of them are real-life examples. The rector of the Radboud University in Nijmegen was accused of sexual harassment. The context: the rector of the university made on a university event 2 comments against a female collaborator. These collaborator had the impression that these comments were a case of harassment. So she made a harassment complaint. A while later, a committee was installed and declared the rector guilty. The executive board and the supervisory board of the university approved the judgment, but decided not to fire the rector, but to keep him in position. And they decided to keep it secret. A year later, years after the event, the collaborator left the university because she was of the opinion that she could not work anymore at the university where those events are kept secret. And 3 further years later, she decided that she could not live with the knowledge about these events and made them public. Some weeks later, the rector stepped down. This was very much debated in the Netherlands, but the entire public debate centered on the question, what kind of comments has he made? Whether it could be sexual harassment, what the motives of the collaborators could have been, and whether the final step of the rector, so his stepping down, was appropriate. We wrote a variety of on this and analyzed the accusation structure. And for us, the important thing were to think about the impact that the initial comments could have, that the further steps are plausible. And particular, we asked whether it was plausible how the board acted. And we were not interested so much in the comments, but the relationship between the decision of the board and the committee to say the rector is guilty and the way they dealt with it. In final analysis, we came to the conclusion that the boards should have stepped down and not the rector. And that only by analyzing the relationship between these different elements of the accusation. A second example, in the Dutch parliament, there has been a former president, Kadia Arib, a Moroccan woman who was president of the Dutch parliament from 2016 to 2021. Perhaps as a background, for a woman with a Moroccan background, it's quite an achievement to become president of the Dutch parliament. And when she came in power, she had to organize the reorganization of the internal working structure of the parliament, which was not such an easy story. In 2022, there were some newspaper reports about possible abuse of power in creating an unsafe working environment by Arib. And the then Presidium of the Parliament under Vera Bergkamp started some investigations. The important point is the basis of these investigations were anonymous accusations coming from some employees of the Parliament. In the entire debate 22, hardly anyone, besides us, made a point of the fact that investigations have been started on basis of anonymous accusations. In 24, some investigations started against an employee of the Parliament for leaking various informations. In 25, it was reported that even the President Bergkamp was involved in the affair. So what is interesting with regard to anonymous accusations here is in the moment where an institution starts an investigation on the basis of anonymous accusation, the institution is itself responsible for the accusation. That means in this case, Bergkamp, as head of the parliament, took the anonymous accusation over, so to speak, by starting an investigation. She was responsible for the start of this investigation, and that makes the situation very much complicated. Nobody asked why it could be appropriate to issue these accusations in an anonymous form. I mean, there can be conditions under which anonymity of an accusation is acceptable. And if that is the case, it must be parallel to a whistleblower. A whistleblower is someone who has some knowledge about something, which he is not expected to make public, but he makes it public because it's the only way to bring these problematic knowledge that he has to deal without endangering himself. That means anonymous accusation, like whistleblower accusations, are justified because the knowledge in question is so risky for the whistleblower or the accuser that this is the only way to deal with it. And what you can see here is investing anonymous accusations may lead to serious harm of the investigator and the institution in which this takes place. In this case, the Dutch Parliament. So we are talking about a very serious situation. And so far, hardly anybody had made a point from the simple fact that the accusation was articulated anonymous. Our third example, where we made now a lot of work about, is the case of extreme accusations. Background: some group in the public, and significantly groups at universities, are accusing the Israel government of performing genocide in Gaza. As you may know, South Africa opened a respective case at the International Court of Justice. Our papers started with a general investigation in the structure of what we call extreme accusations. We identified genocide accusations as an instance of extreme accusations. We reconstructed the relationship between those accusations and the logic of genocide and applied these insights to the Gaza genocide accusation. The problem with genocide accusations has to do with the possibility of validating them. Genocide accusations imply that there is a systematic form of extinction and an intention to do so. And the problem, of course, is how to validate the intention. So how do we know that there really is the intention to organize a genocide? You can wonder, how do we know that the Holocaust was a form of genocide? That could be just a way to understand it. And you could say, okay, in that case, Nazi leaders directly expressed that they have the intention to exterminate the Jews. And in that case, we have specific documents of, like the Wannsee Conference. We know that there were some meetings where people decided to do so. But that is, first of all, contingent. It's contingent whether we have those information. And in some sense, it may even not be the most reliable source. For example, the expressions of Nazi leaders were could have been just exaggerations. Yeah? So the most certain knowledge we have that genocide, the Holocaust is a form of a genocide, has to do with the reconstruction of the logic of the relevant events. So that we see all over Europe in a systematic way, Jews were brought together and transferred to concentration camps where they were systematically killed. And this behavior is not explainable in another way than assuming that there was an intention to exterminate the Jews. Yes, so for example, the logic of the World War II makes it not plausible that the Holocaust was a form of that the Holocaust happened. Yeah, it's in no way explainable by the war logic that one would do these things. So there is no other explanation than understanding it as in the perspective that there was an intention to do just that. The problem with validating genocide accusations is it can take a long time. We have, in terms of legal validation, a politicization of international courts. And we have, so alternative to a legal validation of these claims is a scholarly validation. That, however, requires that the scholars in questions are willing to judge the situation unbiased. And this unbiasedness requires that there are conditions for these scholars to formulate possible different conclusions. They must come to a conclusion it is a genocide or it's not. The problem here is that in the case of our current discussion is that, at least in the Netherlands, those who deny that there is a genocide are accused of being complicit to the Israel government. And this accusation of complicity makes it hardly possible to have an unbiased form of scholarly validation. And this altogether creates a situation where it's questionable whether such a validation is possible at all. If you see this problem, then you can wonder, how does this genocide accusation function? Genocide is considered to be the crime of crimes. Genocide accusations are in so far the accusation of accusation. Genocide accusations makes it nearly impossible to have furthermore relationships. So diplomacy, negotiation, all of that will be difficult if you have such an accusation on the table. And genocide accusation marginalizes all other possible accusations. If the assumption is in the room that there is a case of genocide, then other questions are not discussed anymore. At the same time, we have these difficulties of validation. So we have a polarized reaction. We have a situation where an open discourse is hardly possible. And that means we cannot really see how such an accusation can be issued in a way that it is easily possible to validate it. If such a situation happens, then issuing this accusation is only the articulation of a prejudice. If you I will shorten it a bit up. If you have this in mind, then you wonder, what does this genocide accusation do with the entire situation? The history of Gaza is incredibly complicated. You will already have problems to reconstruct the history of Israel and Palestine. Some people would even say that already the war 1948-49 was the beginning of a genocide. If you are of this opinion, it's hard to see how you can be of the opinion that the existence of the state of Israel is legitimate. And you have the problem in the background that Hamas and other players are denying the Holocaust. You have the problem, what Jan and I called in a paper, the Israel embedding problem. That means that the entire way in which Israel should be embedded in the Middle East is a fundamental problem. And you have the Iran, Hezbollah, and Hamas attacking Israel and denying their right to assistance. So what we have is a situation of a war. That means a war that Israel lead against Hamas in reaction of a kind of war activity by Hamas in 23. And that means to accuse Israel from war crimes, which is something completely different than the genocide accusation. But if you speak about a war crime, you must be capable of saying something about how this war of Israel against Hamas could be lead in another way. And how a war is possible which is not leading to so much casualties as we can find it at the moment. But discussing about a war and war crimes would be something quite different than discussing the genocide accusation. These debate about the way Israel leads its war against Hamas is in some sense marginalized due to the genocide accusation. So what these examples show is that accusations are in some way very fundamentally relevant for human communication, for our social relationship, and these accusations are shaping the form of political debates. Accusations determine how our relationship develop and how they can be developed. And what I talked about was accusation in a way that are only to a very small degree accusation in the legal context. What accusation theory focus on is the form of accusation. we speak about accusation as speech acts that come with an own responsibility. Issue an accusation can seriously harm the accused and the accusee. It can have serious effects on the institutions that takes the responsibility for investigating the validity of the accusation and so on. So understanding this responsibility of issue an accusation seems to be from great importance. These things are much more complicated in context of digitalization, where accusations are articulated in a very unclear environment. So if you think about accusations in former times, imagine how rumors spread in a small village or at a university campus, where issue an accusation happened in a kind of environment that you were able to oversee. In context of social media, for example, it's completely unclear how accusations develop, in which context they are spread, and how they can be controlled. Think about cancel culture or the censorship that we see at US universities at the moment, and you see how important these things can be. So on the long run, I think one could work towards an ethics of accusation. The accusation theory we have developed so far is an attempt to determine the relevant conceptual features of accusations and their social functioning. And by doing that, we have done something novel. This type of accusation theory is not affiliated to a specific academic disciplines. It tries to operate on a very generic level. It's not restricted to a specific type of accusation or specific content, as you have seen. And we can work it out in different directions. So we could think about the logic of accusation, the responsibilities that come with issuing accusations, and the way accusations are handled within different institutional and social settings. All of that could be developed, and that ultimately require a normative theory of how one should deal with accusation in a liberal society, in a globalized society, in a digitalized society. That is quite a challenge. Thanks a lot.
Does anyone have any questions?
Yeah. Right. Thanks, Marcus. Do you have any hypothesis on why it is the case that accusations...
Jan, I can hardly hear you.
Oh. Once more?
A bit better.
I think it's really thank God. Are you sounding? I try again. Is this better?
Yeah.
Do you have any theory about why accusations have not earlier and previously got the interest of philosophers, given the fact that it's so ubiquitous?
I mean, you can say that it's not just not, it wasn't investigated by philosophers, but not as well from any other discipline, yeah? And that has to do that, I think, that people are so much interested in the content of the accusation and not so much in the formal structure. So what we have done is in fact saying, first of all, it's an accusation, independent of what it's about, so to speak. And people were immediately, that you see in all the discussions we have investigated, you see people were very straightforward, interested in the topic of the accusation. And in some sense, it's understandable. In the moment where you speak about genocide, it's such a heavy topic that you don't think about the formal structure in which it's articulated, so to speak. It's so dominant that you directly have an opinion, and it's so, yeah. And but it's in the moment you have thought about it, it's difficult to understand why nobody discussed it earlier.
Right, yeah. Question 2. Moving to board. Hi, Marcus. Indeed,
I can hardly hear you.
speaking more in the microphone. Is it better this way?
Yeah, it's better.
Okay. Accusations are omnipresent already, maybe for a long time, but I have the impression that the amount of accusations is getting bigger. Some politicians make a sport of accusing other people or other groups of anything you can think of. So there is some kind of inflation maybe of this accusations, and people, well, don't bother maybe anymore. Is that something you see happening, and where would this lead to if people don't care anymore? If somebody is accused of something or attacked even as a result of this,
I mean,
how will society develop if accusations, the meaning and the feeling people have, inflate and are well, less felt?
I'm not sure whether there are more accusations.
Okay.
But what I just mentioned right at the end, that the context of social media and so on may have changed something, is perhaps worthwhile of further investigation. I mean, so what I had in mind when I said that is, when I was a child, I spent a lot of time in a shop in a small village in Westfalen where my aunt was selling goods. It was a small village, 100 people. And if someone wanted to spread an accusation in this village, the best thing to do would to enter the shop early in the morning to tell it to my aunt. And you could be certain at lunchtime, the entire village would know the accusation, whatever it would be. Yeah. This context, so I saw the entire morning my aunt repeating the same story over and over again, normally grow bigger the longer the morning took. Yeah, but everybody can imagine this type of situation. Yeah, and what is important here, the context was totally controllable. Yeah, it was these 100 people in this village where the rumor would go about. Yeah, and if you see the difference to social media, you have no fucking clue what's going on if you accuse someone of something. Yeah, you don't know where these thousands of people who are following you, how they interpret whatever they read in your accusation. Suddenly you have fully uncontrollable context Yeah, and then this hyper moralistic attitude of a lot of people brings a situation where, in the combination of these facts, things can explode. Yeah, but they explode in a way that we see in effect a strong polarization of societies in a way that they are hardly capable of dealing with their conflict.
Right, thank you.
So, Marcus, do you see any other example of an accusation that we might study?
I didn't understood you.
Do you see any further example of an accusation worth of investigation?
I think there are more examples, but I think we perhaps should, as a follow-up, think about what would be required in order to develop the theory further. But I think we need a combination of our initial analysis with other theoretical contexts. So I could imagine that connection with political scientists or linguists could be interested in some sense, so that one could work towards a more comprehensive framework. And because so far we developed a bit, the framework just bottom up, but how a bigger understanding of the political implications and so on could work, that would require more theoretical work, I think.
Right, thanks.
Okay, thank you very much, Marcus.
Now, I will start the. Excuse me. I will start my presentation on spinorial forms. This work is attempt to introduce transreal numbers into physics. It was developed by 3 months that I stayed in Rio de Janeiro at the CBPF, Centro Brasileiro de Pesquisas Físicas. And this work was made under the supervisor of Eliel Neto, a great physicist of Brazil, that gave me this opportunity, and for me was a pleasure. It was a very interesting opportunity to do this. I don't have in this work. I don't have the intention to do theoretical physics. This is an attempt to make some kind of speculative physics. In some sense, this work is some kind of philosophical physics or metaphysics. The basic idea is the following: what will be if you have a space-time that is the ground, that is the foundation of our space-time? That's the idea. In such space-time that is the foundation of our space-time, in some sense has nullity, as its nullity nullity is the structure of this space-time. Transreal numbers, but especially nullity. This space-time from which our space-time, the physics space-time comes, has nullity as a point. So the idea is the following. I will make some comments on the test. You have the concept of Minkowski space. Minkowski space is the space in which you have phenomena from relativity, special relativity. it's a special kind of a more abstract space called Riemann space. In such space, Minkowski space, our universe is structured in some sense that every point in this universe is a vector. The vector that are associated with the points of such universe are expressed by the x vector. So you have 4 components: x0, x, y, and z. X0 was characterized as a coordinate in which you have time and velocity of light. So this is our usual form to understand space-time in relativity theory, special relativity theory, where space-time is pictorially I want how to show the here. Okay, thank you. So you have Minkowski space in which each time of such space is a vector of the type that is expressed in the screen. And in such space you can characterize distance, a typical invariant of the physical theories. Such distance is given in a infinitesimal way of expression by the form. You will have ds square equal to c square dt square minus dx square minus y square minus yz square. Such formula is the norm of the space. Such formulas express the distance line between points. This is a typical invariant of physical theories. If you have a reference frame in such region of space-time, Minkowski space-time, and another one in other region, they could explain phenomena, they could measure things, and in such case that you can possibly have no agreement between the measures. But some quantities are invariants, including the distance, this infinitesimal distance that they both have as the structure of space-time. So you have, by seeing this formula, you can see that you can have 3 regions of space. One of these regions where when ds square is equal 0, ds square is minus than 0, is less than 0, and ds square is greater than 0. In the first case, you have null vectors. In the second case, space-like vectors. And the third case, time-like vectors. Each region each region in this partition characterize a special kind of physical space in terms of causality. Null vectors represent the path of light, a beam of light. Space-like vectors are typical are spaces that are outside the observable space. Time-like vectors inside the observable space. You can pictorize and you can show such situation in this diagram. So you have inside the cone, we have what we call our causal world, our observable world. In this world, every information comes to a point from another in a velocity less than the velocity of light. Is our space, is our causal space, is our experienced space, is our observable space. Outside the cone, you have something that are not observable. By any meaning, you have the information outside the cone never reach observer that are inside the cone. In some sense, this region is the region of what we call an unobservable universe. So you and the border are the light paths. So what is the idea in this presentation? You can represent this space, Minkowski space, by using metrics, only metrics. In such case that you have the following situation. If I would, you can see that in the. So you can now you can present each point of Minkowski space as you can present every point in Minkowski space parameter as a function, as a space whose bases are these metrics. So you have this one in this situation. You have this. Every vector could be present as a matrix of such form. So this is our space-time presented as a matrix. A matrix is very interesting because you have in these matrices complex numbers, etc. The determinant of this space is equal to that form. So you can see that the determinant is equivalent of the metric of Minkowski space. So what is the idea that I will present? There is a theory about spinors. Spinors are particles that live in a very abstract space. If from spinors, our space-time comes. Spinors are complex numbers. They are introduced by Elie Cartan and later by Weil and Dirac. I think that spinors are very important to understand quantum particles or something like that. The idea is the following. Our space-time comes from spinor in the sense that these metrics that you see above could be identified with two metrics of product of two metrics in which you have spinors. So you have this in the page, in the following page. So you have that you can see that x could be equal to this matrix, and this matrix is ct plus z, x plus I y, etc. equals to this product of spinor. The first column, the first matrix, is a column matrix in which you have complex numbers, spinors. And the second matrix, the line matrix, column matrix, is another matrix in which you have the conjugate terms of such complex numbers. So if you replace in the first matrix these values above, so you have that you can construct our space-time by means of spinors. In other words, spinors are the brick from which our space-time comes. So there's not more basic than spinors to understand our space-time. Spinors live in another space-time, in a space-time that you have that obey Lie and Clifford algebras, a space-time that is made up from complex numbers. If from this space-time our space-time comes. Now a basic question is, there is something more basic than spinors. I could postulate a space-time where something some physical and some entities, mathematical entities, are more basic than spinor, and from which spinor come. So now the idea, my answer for that question is it is the case. So I introduce in a very speculative way the concept of spinorial forms. What is this? So you see here that spinorial forms are entities that lives in a set that I call Spinorial forms. In this set, we have two members, nullity and a matrix compound by psi1 and psi2. Psi1 and psi2 are spinorial forms. But what and nullity lives there too. So you have trans-spinorial set as a proto space, more abstract than the space where live spinors. And from such space, from such set, spinors comes, and from spinors comes our space-time. So you have this situation. Trans-spinorial sets cause spinors, and spinors cause Minkowski space. And this trans-spinorial set has nullity as its member. So nullity now is seen as a special kind of point of space from which our space comes. In this sense, I will try to transform nullity into a great and metaphysical void from which our space-time comes. It's very speculative. I don't have the intention of doing theoretical physics, but I have the intention to present some possibilities from which you can introduce nullity as a very interesting physical theoretical element. So what is this spinorial forms are? Spinorial forms. So you see that from spinorial forms, I must take complex numbers. So each spinorial forms acts in nullity, and the result of that action is such complex number here. Now there is something that I must explain. This symbol, real numbers between this special kind of parenthesis. I don't know how is the English word for this. Angular rects represents nullity. Nullity here is seen as some kind of sets of real numbers and superposition. And spinorial forms act as an operator that take from such set in superposition just one real number. Let's see that a spinorial form 1 choose two real numbers. The first one is a real number, pure real number, and the second one is the real number that is associated to a imaginary unity. So spinorial forms 1 by means of his iteration, but by means of his operation nullity, I have a complex number. Spinorial form 2 acts on nullity, and by means of such action, I have another complex number. Because spinorial form 2 with the sign asterisks acting on the reals on superposition nullity makes has transformed this situation in a pure real number. And spinorial form 2 with asterisks acting on nullity. Nullity now is identified with the superposition of all real numbers, gives to me the real part of a imaginary part of a complex number. So spinorial forms 1 and 2 give to me two complex numbers. These two complex numbers are in fact two spinors. Spinors are complex numbers. So you have two spinorial forms, both act on nullity, so I have two complex numbers. And these complex numbers are spinors. There's no rule, there's no mechanism to determine which number, what number will be, what complex number will be. So in some sense, there is the postulate here that Spinorial forms acts in a way that this X is free. Is a very degree of freedom in such situations. So you have, by means of that, you can construct spinors by means of such action of the spinorial forms on nullity. So you can have this one. You can have such calculus. You can have these expressions. And now, well, what is the conclusion I have of this work? If you admit that the universe has nullity as a component, as a point in space at nullity, maybe you can consider that our space-time, that space-time in which you have points in which you have continuity, causal laws, comes from this point at nullity. Philosophically, I believe that the notion of transreal numbers give us the possibility of a new way of understanding the universe, by means of which this new way implies that our physical universe is not is a possible world that comes from nullity. Nullity is the place where our universe comes, and the mechanism to do this in this work is by means of spinorial forms. Spinorial form acts on spinors. Spinors gives the space-time, so you have such situation, this transivity. Spinorial forms cause our universe by means spinors. It's just a speculative work that I did in Rio de Janeiro, but in some sense for me opens the possibility of treating nullity as a very as an interesting component of physical theories, speculative theories, in which you can say that the notion of a universe beyond our universe is totally understood by means of nullity. So that was the essential of my presentation. Very, very short. And I open to comments and questions.
Yeah. Can you say which properties of nullity are essential for your story? For instance, is it important that 1 divided by 0 is null, that 0 divided by 0 is nullity, or are other properties of nullity the key to your story?
The essential property is the following: nullity is a geometrical point. I think that this idea comes from the test that you have points, that you have things that are in nullity outside the space-time. Nullity is not just a name of such arithmetic operations. Nullity has a very typical position in the realm of space-time. In this sense, I think that if you have a system of reference whose coordinates are nullity, 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 you are dealing with something that for me is almost theological. Is almost the position of God in the universe.
Does it make sense that in a four-dimensional space, say 2 out of 4 coordinates are equal to nullity and the other ones are not? So is it either nullity full screen or may it be partial nullity?
No, I think that the point in nullity is enough.
Just one.
Just one. So you have in this case an absolute system of reference from which a possible universe, including our universe, comes.
But you could imagine more complicated models where different 2 dimensions or 3 dimensions may equal nullity. and the last dimension doesn't.
Yeah, the idea is, in some sense, we have a point whose coordinates are nullity. Just one point.
Just one.
So you have in this sense, if you are in the physical universe, you have a lot of system of reference whose coordinates could be described as 0, 0, 0, 0. So you have a system of reference, a lot of them whose origin is the same, 0, 0. But there is one unique system of reference in which postulately you have you have nullity, 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 nullity as its coordinates.
The coordinates of its origin.
Yes, the origin of such system. And the spinor forms in some sense lives there. And from spinor forms you construct spinors.
But the spinal forms a spinor paired with nullity.
A spinor forms is the operator that acts on nullity to give to me spinors.
Okay.
Nullity is the basic point. In this basic point, I have spinor form that acts on nullity. And from such action, I generate two complex numbers that are the spinors. So the rest, if you have spinors, the story goes as you have.
I see.
It's just an attempt to put nullity into a very interesting theoretical theory, in the theoretical physics. But I know that it sounds very metaphysical. But
Yeah, it's a matter of taste.
but I think that there is no problem. But at least I have the impression that every scientific theory has some kind of metaphysical stuff in some sense.
Always, yeah.
Okay.
So I finish here.
Yeah.
Okay, well, the plan is that I give a short update on aggregation dynamics now, because there's some spare time. Thank you for giving the opportunity, James. Move to the next slide. Won't move to the next slide. Yeah, you have to position the mouse on another place on the screen.
Yeah.
Okay. 2 years ago, the paper with the title you see in the screen was published in Transmathematica, and it is about aggregation dynamics. I will recall quickly what it's about. Aggregation dynamics totalizes ecology, one could say, and this works in the following way. We're used to partition the world in organisms and things. I see a small typo over there. And aggregations allow many more forms to play as actors in this theory. So any fragment of reality and also imagined beings could be actors in some mind of some being. So aggregation dynamics looks for patterns in the behavior and structure of interacting in aggregations. And most of the time, these aggregations are limited cognitively in computing power or in information, and also materially in the material they can access and the energy they have to go about. The idea is that the world around us is structured recursively, and that think that given this idea of the assumption, you can start anything everywhere looking for patterns. And I decided to start with the empirical focus on people and the problems and solutions that keep them busy all day. And the main hypothesis
at this stage is the innovation illusion that says that after some abstraction, it appears that people always solve the same problems and do so with known solutions that belong to these problems. You can also speak of problem types and a repertoire of solutions. So after the publication of this paper, it was containing a lot of information and concepts, I felt the need for substantiation of the motivating examples and further application and testing of the terminology. And I made a start with 2 papers on the Los Angeles County smog control case. This is an interesting piece of history. In Los Angeles, smog became a real big issue in 1943, and society and politics started moving and complaining and finding and looking for solutions, and it took quite some time to improve the situation. Also, technically, there were a lot of developments, for instance, in the motor technology. So there's a lot of problem cases and a lot of solutions that play a role in this case. And it's, for another reason, it is interesting because the problems and the problem situations that you encounter in this case carry over to the current time, because air pollution is still a problem, and the scope is expanding because CO2 is now also a problem, and it is also getting international as a problem, and that brings about repetitions of problems that we problem situations and solutions that we see on a smaller scale already in this case. So it gives a lot of basis for further work, and I thought it was good to document the case and test a lot of terms on this case. I'm happy to say that it will be out in some time. Now, what's the current work on aggregation dynamics? Of course, current phenomena need to be need to find a place in aggregation dynamics with his total aims. And a current phenomenon that is attracting a lot of attention is, of course, ChatGPT. So what can we say about this viewed from aggregation dynamics? In the first paper, a problem propagation is defined as a history or projection of future actions reduced to problem types and solutions. And it can be depicted as a directed graph. So for instance, you start with problem P1, you solve it by solution S1. This changes the world, and in this changed world, again, problems pop up. P2 here and P3, which are solved again, and okay, this new situation, of course, will lead to other problems, etc., etc. Clearly, given the fact that the problem types and the solutions are limited sets, you will find patterns in these problem propagations. At least you will find time and again the same problem popping up and the same solutions applied. But I think there are much more problems. Now assume that we can make it plausible that problem propagations, informal arguments, and human texts, the majority of them, are essentially about the same thing. Then one could say that if you pose a question to ChatGPT, you seed it with a problem, and it will develop a problem propagation in its neural network. And what comes out of it is a text, and these texts appear readable to us and plausible and useful because they follow a format that a type of argument that we are very familiar with. It copies what we used to do. So you can say that ChatGPT in a way proves the innovation illusion or gives reason to think this is not complete nonsense. How can you view such a system as ChatGPT? Well, it is very similar to what we see with every introduction of a technical solution. Most technical solutions start out with copying the behavior of another system. You could call it a simulation. And after some time, when it's used, not the inventors, but the people that grow up with it, see different possibilities with this new tool, and then other uses become apparent. So ChatGPT is, I think, ecologically not something new. It is a well-known type of addition to the world. Whether it is an innovation is not clear to me yet, but that is a question to be discussed in this paper. What also is from evolution, well-known situation is what we see happening with people using ChatGPT. One could say, isn't it surprising that something that bothers people and they don't know how it works, it worries them, but still they just use it and try to use it to their advantage. And in evolutionary theory, it can be argued, and it is argued, that for A, using B in competition with C, limited or no knowledge on how B internally works is often sufficient. And even having more information about the workings of B can be counterproductive. So the situation, what we see when people use ChatGPT without knowing anything about it, but just using it in competition with others, is a very usual situation. Nothing new here. Okay, that was a short update on aggregation dynamics. Thank you for your time. Any questions? Okay. Are there any questions? It gives you more time to think.
So the question I always have, your aggregation dynamics describes people on a treadmill, always going round, solving a problem, new problem, solving a problem, new problem. Do you see any hope of getting off the treadmill?
No, I don't. We are in the large picture. We are in a trap producing entropy, and we cannot escape this trap and this treadmill, but we can use the energy that we have available in a smarter way. So we can slow down the treadmill, I think, and we can make one another less crazy the whole day, and maybe more happy.
Isn't an innovation stepping out of the treadmill?
No, that's not. You step into another treadmill.
Okay.
Yeah.
So
A main question that I have: what is innovation? When do you speak of innovation and real innovation? Of course, there is innovation, otherwise we wouldn't be here.
But yeah, okay, but of course, an innovation may start subsequent treadmill,
Yeah.
but you step out of the treadmill that you are in.
Mm-hmm.
You change treadmill.
Yeah,
so to
yeah,
say.
yeah.
Yeah. But how to see an innovation? That's difficult.
That's
That
difficult.
can
Yeah.
only be done in hindsight, probably.
So we yeah, there's a lot of fuss about innovations. We have the whole day we have innovations, but okay. I say, okay, there's very little innovation, but a lot of repetition. And the question is, where is the real innovation?
Yeah, of course,
Yeah.
with ChatGPT, we see many lookalikes.
Yeah.
The whole thing starts showing this behavior
Mm-hmm.
quite intensively. And it's used by people who don't understand it, clearly.
Yeah.
That's no problem for them.
No.
Right. Yeah.
Okay, thank you.
Thank you. Okay, so this is the last talk. I'm James Anderson, and here we go with a description of the Principia Transmathematica, which is a book that I've just written. So I started off since the last conference by writing this book, Built on Sand, How to Divide by Zero and Thereby Save Science from Guaranteed Failure. The idea is that arithmetic fails on division by zero, and that cascades into errors in pretty much every science. This book is partly biographical, and it describes my thinking at the point I was moving from the usual paradigm of science into the transmathematical view of science. Recently, I've published this book, Principia Transmathematica. It's a popular science book. It has a bit more detail than is normal in a popular science book. It describes transmathematics, and it's not concerned with the old paradigm. It's me having pretty well moved into the new paradigm of science. I have plans for the book that the book should summarize transmathematics and trans science. So the first edition, that's this one, was written by me. The second edition, I have invited people who have researched with me on transmathematics or any total systems. And the third edition, I'll invite anyone who's published on any total system. And the idea is that authors can maintain their chapter over many years, so it becomes a summary or an entry point describing their life's work. The idea of the Principia Transmathematica is that the general public can appreciate trans science. If you read the book, you'll see what we are doing. There is quite a bit of detail in the book, enough for an undergraduate student in mathematics, physics, computer science, and philosophy to read the book and then start their own undergraduate projects. 16-year-old children can teach themselves transreal arithmetic and trans-Newtonian physics from what's in the book. And some 16-year-olds have already done this. You need to understand Newtonian physics before you can understand the trans-Newtonian. In fact, somewhat younger children have taught themselves transreal arithmetic, and the youngest person in the world is 10 years old. So a 10-year-old sat down and learnt transreal arithmetic. And parents and teachers can learn transreal arithmetic and then teach it to their children, and I suggest from the age of 4. In England, it has been taught in school to children from the age of 6, but I think they could have started earlier. Mostly, I see the Principia Transmathematica as a blueprint for me. It's me laying out all the pieces of the jigsaw puzzle, and the subsequent editions, my chapter will be how I put those pieces together. Other chapters are entirely up to the other authors. The book has an introduction to total systems, of course, there is a notion of trans-symbols which generalize the notion of symbols. Symbols at the moment are discrete and finite, and I consider the possibility of what would happen if you had a continuous symbol. There is a notion of translogic. I'm going to talk about this in a little later. And again, I'm arguing for totalizing logic. I'm going to say that there are limitations to the logic we use in mathematics, and that turns into limitations in the way we use sets, which are answered by totalizing the notion of sets. There's a short section on the philosophy of totality, and then there is about 12 pages on transreal arithmetic. It's enough to learn transreal arithmetic for that. There is a very brief discussion of the empty symbol, which is related to bottom, but appears to be more general than it. It's discussion of transphysics, specifically trans-Newtonian physics, discussion of transcomputation, particularly on trans-2's complement arithmetic and trans-floating point arithmetic, which I claim have advantages over the standard ways of doing things. So that's what's in the book. What I'm going to talk about now is trans symbols, translogic, and transets. I will briefly mention the arithmetic for children and show that you need to learn 12 steps to get you from real arithmetic to transreal arithmetic. And finally, I'm in a position to formalize the paradigm of transmathematics. So up until now, we've just said transmathematics is about totalizing functions. And now I can give you a much more specific definition in formal terms. So what you're going to see is a story of my thinking that leads up to that specification, that statement of what transmathematics is. So very quickly then, we'll go through each of these topics. A trans symbol is a point that is anywhere on the unit line. And you can do a surprising amount of stuff with the unit line. For example, in theory, but not in practice, we could take all of the texts that have been written up until 9 o'clock this morning, girdleize them in the big number G, compute 1 over G, and mark that position off on the unit line. So that point would be a specification of all human written knowledge. And I'm told that this is the story of a science fiction book. So if anybody knows what that science fiction book is, please do tell me. Now, to the right of this 1 over G, there are rational numbers, some of which happened to be earlier states of knowledge, so everything written until 9 o'clock yesterday, and some of them have never been used. Everywhere on the line, there are irrational numbers which don't relate to written knowledge. They're some other kind of knowledge. And the question is, can we exploit, for example, calculus to access that knowledge which isn't accessible via text? Now, it turns out it's simpler to define trans symbols on the transreal number line using only 0 and a less than relationship, because we don't also need a unit line, a unit. So we can, just with 0 and less than, we can define tetrachotomy. And that's a simpler thing to do than defining the unit line. Okay, trans symbols. A definition: alpha is an atom if and only if alpha is a member of atom alpha and the cardinality of alpha equals 1. Many set theories have used atoms. Normally, if a set is reflexive, alpha contains alpha, then the cardinality is infinity. And by saying that the cardinality is 1, I'm saying there is a singleton object that contains itself. This is very similar to, well, the quine atom is one such object. There are many more objects in the definition I've just given you. So that allows us to introduce atoms into a set theory. The reason for doing it this way is that it instantly totalizes all the set connectives. So if you want to say, what is the union of alpha 1 and alpha 2? The answer is, it's the set that contains alpha 1 and alpha 2. And you haven't changed any of the definitions of the set theory. Most people who introduce atoms change the definitions, or they leave them so that they don't apply. Some of them don't, like union, doesn't apply to atoms. Now that's okay if what you want to do is prove theorems in your set theory. It's not okay if you want to totalize it and prove meta-theorems in your set theory, because you would much rather have it the case that all of the operators apply to any kind of object. And this notion of having an atom obey tetrachotomy immediately generalizes the transdedekind cuts from real numbers to trans symbols. So we have a construction of the transdedekind cuts into the parts inside a set, on the boundary of a set, outside the set, and in the background. And I asked the question, can we obtain trans-surreal numbers this way? I know the answer is yes. I'm just putting the question out there to attract postgraduate students in mathematics to take on the issue. So a set theory with atoms has enough cardinality to describe proper classes, and there are many such set theories known in mathematics. But just putting atoms into a set theory doesn't give you the ability to directly encode antinomies, paradoxes. So you can't directly include the class of all classes, which includes antinomies. So just having atoms gives you enough cardinality, but not enough structure to describe the class of all classes. Right, here is a bizarre result from computation theory. All Turing computable functions are continuous, piecewise continuous. So the question I have is, can they be approximated by a Fourier series? Can you approximate any computation by a Fourier series and add up the components of the series? I did some work on that. I didn't get very far.
Computable approximation.
Yeah. Now, you've just raised the issue of computability. Is it a computable approximation? If we accelerate over trans symbols, then we can have an accelerated Turing machine that solves all problems, all programs, even if they're not Turing computable. And most of this is already known. So the idea of acceleration has been known for a long time. It's been known from before Turing specified the Turing machine. So what we do is we complete one instruction at time 0. At time n, we compute 1 over 1 minus n Turing operations. So at time n equals 0, we've done 1 operation. And at time 1, remember I'm working on the unit line, we've got 1 over 1 minus 1. We've done infinitely many instructions at the last point in time on the unit time. Now, acceleration has been used before, and people bumped into a problem that whilst you accelerate the number of operations, the amount of memory the machine uses can grow unboundedly. The solution to that is to accelerate the memory storage as well. So if you start off writing into a Turing cell, Turing specified that there were squares on his tape. If you make the width, the side of the square 1/2 each time, then you can have infinitely many pieces of data stored in a finite amount of space. And if you do that, then it decides all computations. So we're in the happy position in theory, but not in practice, in theory, of being able to say whether a computation will succeed or not. So mathematics uses a finite number of discrete symbols that don't have sufficient cardinality to write out a proper class. You can specify a proper class, but you can't write out its elements. Transmathematics uses the greatest number, it's a transreal infinitude of continuous symbols that do have sufficient cardinality to write out the class of all classes. So my conclusion is that a finite number of discrete symbols is an inadequate foundation for mathematics and transmathematics, but the greatest number, a transreal infinitude of continuous symbols, is an adequate foundation for mathematics and transmathematics. Do wait for the last slide. This is going to be more acceptable when we come to the end of the talk. So beyond the book, mathematics names logics by the number n of symbols. So mathematics says that binary logic has two symbols, f and t. Translogics, by contrast, are named by the number of combinations of symbols, so 2 to the power n combinations of n symbols. So a quaternary translogic has 2 to the power 2 equals 4 combinations of symbols, which are gap, false, true, and contradiction. And the quaternary translogics are tetrachotomous. So they've embedded this notion of tetrachotomy that was embedded in symbols and is embedded in the transreal number line and is embedded in the notion of transets. So it's a common theme running through transmathematics. Now, I maintain that mathematical binary logic is a partial system. It's missing 2 states. Therefore, it's guaranteed to fail somewhere, and it fails on gaps and contradictions. Now, of course, I know that mathematicians know about gaps and contradictions. By and large, they tend not to put them into the truth tables, and that's a problem. So as a matter of vocabulary, all translogics are total. Therefore, they're not guaranteed to fail. So I'm building up on the story of built on sand, which is removing the guarantee of failure. And when I get to the last slide, I'm going to be in a stronger position. I'm going to claim that transmathematics is guaranteed to succeed. Very strong claim. And let's see the journey toward that claim. So logic with n equals 1 symbols is a total binary translogic with 2 to the power n equals 2 to the power 1 equals 2 combinations of symbols. For example, if we have the symbol f, we generate the states gap and false. If we have the symbol t, we generate the states gap and true. All translogics are total. We're dealing with all combinations of the possible outputs. Therefore, they're not guaranteed to fail. A logic, so this is a logic, not a translogic. A logic with n equals 1 symbols is a total binary translogic, which has 2 to the n equals 2 to the 1 equals 2 combinations of symbols. The symbol f generates the states gap and false, and true generates gap and true. Binary logics implement confirmation bias. So if you fail to witness the truth, if we've got a binary logic that's looking for truth, if you fail to witness truth, then you have a gap. If you have one or more witnesses of truth, then it's true. But if you have one witness of truth and then you add any number of failures to witness truth, it doesn't change the outcome. So there's no way of going back from true to something that's not true. And similarly for witnessing falsehood. Now, my claim is that confirmation bias is not faulty reasoning. It's correct reasoning in a binary translogic. Now, binary translogics are the simplest logics that change state. So it's the simplest logic that has survival value. And because binary translogic is the simplest logic with survival value, it's the most likely logic to be instantiated by evolution. It's the most likely logic to turn up in animals, plants, and us. Combining the output of a total binary translogic that seeks truth with the output of a total binary translogic that seeks falsehood gives a total quaternary translogic that contains binary logic, which mathematicians use, but it's not guaranteed to fail. So we've totalized the notion of mathematical logic using 2 binary translogics. And I maintain that classical Boolean binary logics are faulty. they're guaranteed to fail somewhere. They fail on contradictions and gaps. So my conclusion at this stage is that binary logic is an inadequate foundation for both mathematics and transmathematics. Binary logic followed by quaternary translogic is an adequate foundation for both mathematics and transmathematics. And in future, theorem provers might rebase mathematics on translogic. Now, this is a very important technological point. So it's possible to prove theorems using a computer. The effort of producing a formal proof is measured by something called the Brouwer ratio. And for a human being, it's about 40. So if a human comes up with an informal proof and wants to make it formal, it typically takes 40 times as much time, which means that in one working lifetime, a human mathematician can do 1 year of creative thought and 39 years or 40 years of formal proof. Mathematicians tend not to work that way. They do many years of creative thought and use informal proof methods. So there is a huge advantage to using theorem provers that do that work for the human mathematician. Now, at the moment, if you take papers from mathematical journals and check them with a theorem prover, you find that 20% of the papers are correct and 80% are faulty. So 80% of the mathematical literature is faulty. It would be a very good idea to have theorem provers to check that mathematics. And if you've got a theorem prover that can check a big body of mathematics, you can change the basis that you start from. So you could start from binary logic, you can start from counting. I'm suggesting you could start for translogic, and it would just be a press of a button that the system would take care of rebuilding all of the mathematics that you've chosen to put into it. So let's move on to transets. The transset membership function and all transset connectors use quaternary logic. So transset theory is immune to the antinomies of set theory by its structure. And on this slide, I've got a picture to give you a mental model of what a transset is. Maybe I can show you in the book. Yeah, that's the picture. Right. So I've drawn, yeah, it's in there too. So page 17. So I've drawn a cone. The cone has a background, which is the apex of the cone. The base of the cone has a boundary which divides the base into an inside and an outside. I call the apex of the cone the background. Everything on the base of the cone is the foreground. Now we can map our quaternary translogic onto the membership function. So if we have a gap, you're in the background. I've given the name in German as well, Hintergrund. I'll tell you why in a moment. If the membership function is false, you're in the exterior, which is the same as set theory. If the membership function is true, you're in the interior. And if the membership function is a contradiction, you're on the boundary. And that is a paraconsistent transset theory. And it classifies all possible outcomes. So all possible combinations of true and false occur somewhere in that set theory. Now it's useful to note that every transset with an empty boundary is a set. So we're taking over, absorbing the whole of set theory. Every transset with a non-empty boundary is an antinomy. So now antinomies are first-class objects in our transset theory. The interior of every transset is a set, the exterior of every transset is a set, and the background of a transset is everything that is not in the foreground of the transset. I realize I forgot to tell you why I use Hintergrund for background. It's common in mathematics to use R. So if you're dealing with complex numbers, you use R for real numbers, I for imaginary. You have a function with that single letter name. In English, I've bumped into the problem that background and boundary have the same initial letter. So by calling background integrand, you have the option of having a function h that accesses the elements of the background. It's a very minor reason for doing it, but maybe it'll help someone. So we can choose to make the transet of all transets an antinomy. You've got quite a lot of choice about how you handle. Oh, no, okay, sorry, I've confused myself. We can choose to make the transet of all antinomies an antinomy, whence its interior is the set of all antinomies. So you can have a well-formed set in the usual set theories whose elements are antinomies. And similarly, we can choose to make the transet of all background elements an antinomy. You do have a lot of choice about how you handle background elements. I take the view that numbers and logic is physical things. So for me, a number is a physical configuration whose systematic transformations obey the rules of arithmetic. And that means that the background contains the physical universe, which is why you've got so many ways about how you handle the background. However you handle it, if you've got a transet of the background elements, you can take its interior, which is a conventional set of all the background elements. And we're going to see how that resolves, how it dissolves the problem of the Russell transet. So what I'm going to do is translate the Russell set problem into transets, solve it in transets, and then show you how you could do it without explicitly setting it up in the notion of transets. So let's start. The Russell transet is the transet of all transets that are not in their own interior. We say that a transet is in its own interior, has the property that it contains itself. So now the Russell transet is the transet of all transets that do not contain themselves. So I've translated Russell's specification of the transet into the Russell set into transets. So what is this object? All objects that are not transets are in the background. All transets that unambiguously contain themselves, such as a universal set, are in the exterior. All transets that unambiguously do not contain themselves, such as the empty set, are in the interior. And all transets that ambiguously contain and do not contain themselves, such as the Russell transet, are in the boundary. Now here's the take-home message. The unambiguous Russell set is the interior of the ambiguous Russell transet. So you take the Russell transet, it has elements in its boundary, which are antinomies. You take the interior of that transet, and it is a conventional set which contains all of Russell's elements, unambiguous elements. We can do exactly the same with ordinal numbers. There is a paradox that the set of all ordinal numbers is a bigger ordinal, and so you imagine you cannot construct the set of all ordinals, but we're just about to construct it. So the transet of all ordinals is an antinomy that lies in its own boundary. The set of all ordinals is in the interior of the transet of all ordinals. And the transet of all ordinals is the greatest ordinal, which we call transordinal infinity. The transet and set of all ordinals both have cardinality infinity, and that dissolves the paradox of the set of all ordinals. So what we end up with, we have a paradoxical object, which is the transet of all ordinals. Its interior is non-paradoxical, it's unambiguous, it does not contain itself. Nevertheless, that set is itself the greatest ordinal. And we can now replace proper classes with transets. We're not forced into a position of going beyond the notion of a set in order to handle the class of all classes. which is good because it means in secondary school you can teach transset theory to people, and then you don't have to upgrade in university to discussion of classes. So now we can arithmetize this. The membership function, if the membership value t is nullity, you're in the background. If it's greater than 0, you're in the exterior. If it's less than 0, you're in the interior. And if it's equal to 0, you're on the boundary. And that is a fuzzy transset theory. So I come back to Walter and his discussion of fuzzy transets. And transets are structurally tetrachotomous, the same way that trans symbols were tetrachotomous, the same way the transreal number line is tetrachotomous, the same way that, yeah, I've said it, the transset theory is a tetrachotomous. Right. Every transset embeds in a tetrachotomy. And that means, because we can write mathematics down in sets, it means that every part of mathematics, transmathematics, physics, and transphysics embeds in a tetrachotomy. And that changes our notion of what measurement is. So up until now, measurement has been measurement on a scale. And now I'm adding a fourth case, which is that an object can be unordered. So you can be on the scale or you can be unordered. So that's quite a big claim that I've changed the notion of what measurement is. Now, the universal transet, we can take it as an axiom that the universal transet T exists such that every transet is exactly one of the interior of T or the boundary of T. If we have a universal transet, we no longer need trans symbols because the trans symbols already exist in the universal set and we can get them by separation. The universal set is problematic in some set theories, but now it's just the interior of the universal transet. So we have a conventional set which is an unambiguous set that contains all of the elements of the universe. And separating the universal set from the universal transet dissolves all the antinomies of set theory. So again, I'm escaping from the antinomies by allowing them, but allowing them in the transect structure, which is tetrachotomous and deals with all possible combinations of true and false. Right, we're now at the position where we have the axiom of total comprehension. For all quaternary translogics, the predicate phi of x, it is the case that x given phi of x exists as a transet. So every possible logical sentence induces a transet. Now that means we no longer need the universal transet. And we no longer need proper classes. So we're now in a different position. So the usual set theories, the Miller-Frankel set theory and so on, are grounded set theories. You start from the axioms, you build up, and you can't get to a universal set in that particular set theory. There are set theories that have a universal set, but they're ungrounded. You can't get all the way back down to the axioms. And now what I'm saying is you can start anywhere. You can start at the ground. You can start, let's say, in the sky with a universal set. You can start absolutely anywhere, and I call that a free theory. So trans symbols, translogic, and transets are bijective and potentially homeomorphic over tetrachotomy. I'm opening up the possibility of doing topology, of doing calculus on things that are not knowable in text and writing down those solutions as symbols or indeed as transets. And all mappings are computable with an accelerated trans-Turing machine. And I need that theoretical ability to recognize when a gap occurs. So when you call a function and it has no return value, I need to be able to know that there is no return value without having to wait for an infinite amount of time, as I would with a Turing machine. So the conclusion is that set theory is an inadequate foundation for mathematics and transmathematics. Set theory is an adequate foundation for both mathematics and transmathematics. The trans symbols can be obtained by separation from the universal transset, so we don't need them as primary objects, first-class citizens. And in future, theorem provers might rebase mathematics on transets. So I'm not expecting that anyone is going to rewrite the theorems of mathematics in transmathematics. Nobody's going to do that. But when we have the technology to have large bodies of mathematics entered into theorem provers, it would be possible to make that change as a technological activity. So 4-year-olds, infinity, what can you tell a 4-year-old? And I've gone back to the Piagetian stages of development. You can tell a 4-year-old that infinity is a number, and you can show them how infinity is written. You can tell them that nullity is a number, and you can show them how nullity is written. And that's it. It's a number. The child is about to develop the ability to count. At 5, you can tell them that infinity is the biggest number, and that's a change from the usual mathematics. Usually in mathematics, you don't have a greatest number, but now we do. And you can tell them that nullity is not bigger than any number and nullity is not smaller than any number. And I've split these out into separate statements because at 5 years old, children can't handle logic like or and. 6-year-olds, maybe you can tell them that infinity plus a number is infinity, infinity times a number is infinity, nullity plus a number is nullity, and infinity times a number is nullity. The idea of a number here is the sort of numbers that a 6-year-old child would know. It's the things they can count on their fingers. At 7-year-old, you can start telling children that infinity times infinity equals infinity, infinity times nullity equals nullity, and nullity times nullity equals nullity. At 8 years old, you can tell them that 0 times infinity equals nullity, 0 times nullity equals nullity, and infinity minus infinity equals nullity. In England, by the age of 8, most children have a sophisticated understanding of infinity. It's a very, very young age to understand the concept of infinity. And what I'm proposing is that we teach children the transreal infinity and the transreal nullity. At 9 years old, you can teach them that infinity minus n equals nullity, and infinity minus infinity equals nullity, and nullity minus nullity equals nullity. By 10 years old, it's already too late for your child to be the youngest person in the world to learn transreal arithmetic, because a 10-year-old has already done it. In fact, in England, a 6-year-old child has passed the secondary school mathematics exam. So there's a national exam, and a 6-year-old has passed it. So there are some 6-year-olds who could learn the whole of transreal arithmetic. Where they are, I have no idea, and what they will do with their lives, I have no idea. But there are some geniuses out there. So transreal arithmetic, let me step through the 12 steps that you need to take to go from real arithmetic to transreal. And you start off with a frac term. You say that n over d is the transreal number, which is the real number n divided by the real number d. So instantly you can divide by 0. So 1 over 0 is the number 1 divided by 0. So I'm identifying frac terms with frac values in your term. I do find your notion of frac terms incredibly useful. And I will certainly think about the things you've said today. In the canonical form, the sign of a trans number is carried in the numerator. That's already an operation of rational arithmetic called rectification. You convert the number so that instead of having a negative denominator, you have a negative numerator. Only positive finite factors are cancelled between the numerator and denominator of a transreal number. Here is multiplication. A over b times c over d equals a times c over b times d. That's what we already teach children in school. No modification is needed. Division, we already teach A over B divided by C over D equals A over B times D over C. And we need to remind people to rectify the results. So if C is negative and you're turning it into D over C, then you need to move the negative sign up to the numerator. Addition works like this: 1 over 0 plus 1 over 0 equals 1 over 0, 1 over 0 plus minus 1 over 0 equals 0 over 0, and minus 1 over 0 plus 1 over 0 equals 0 over 0, and minus 1 over 0 plus minus 1 over 0 equals minus 1 over 0. So we're adding infinities using the existing rule of adding fractions with a common denominator. So we're not saying anything new about how to do addition, but we're saying something about the conditions under which you're authorized to carry out these additions. Otherwise, A over B plus C over D equals A times D plus C times B over B times C. And again, we already teach that in schools. And all I'm doing is changing the circumstances in which you're authorized to do addition that way. Transreal arithmetic is associative, is a property, now that we've specified transreal arithmetic, that it is associative. It's a property that it is commutative, but it's only partially distributive. And if you're looking at the slide, you'll see I've written out one of the rules in red because I forgot to put it in the book. That's why it's in red. So transreal arithmetic is partially distributive. A times B plus C equals AB plus AC when A is not equal to plus or minus infinity. The case I forgot, when A is equal to plus or minus 1 over 0, and B times C is greater than 0. In other words, when B and C have the same sign, both positive or both negative. And otherwise, when A equals plus or minus 1 over 0 and B plus C over 0 equals nullity. There are some non-trivial solutions to B plus C over 0 equals nullity, which are, for example, that B is minus infinity and C is plus infinity, or B is nullity and C is anything you like. And it amuses me that the number nullity turns up in the specification of partial distributivity. Despite the fact that transreal arithmetic is only partially distributive, it's still total because you can calculate every sentence of arithmetic. 11th step, we assert tetrachotomy. Every number is one of less than 0, equal to 0, greater than 0, or unordered. And I've backed off from saying nullity. And the reason I've backed off is to do with translogic and transset theories. There may be many atoms that have the property that they're unordered. The usual set theories that have atoms are unordered. So I'm allowing that possibility, as well as allowing what is certainly a very rarely examined situation that atoms are ordered. And again, I've changed the notion of what it means to be a measurement. Measurements can be on a scale or they can be unordered. Now, if I assert that 1 over 0 is greater than 0, I do that so that minus 1 over 0 is less than 0. So if I make this assertion, 1 over 0 is greater than 0, we can prove that 1 over 0 is the greatest transreal number. And it follows from that that minus 1 over 0 is the least transreal number. And I assert that nullity, 0 over 0, is unordered. So having taken nullity out of the definition of tetrachotomy, I now have to associate nullity with the fourth case of being unordered. And I do that so that I can have many things that are unordered. So now that we know that 1 over 0 is the biggest number, we may as well define 1 over 0 as infinity. Now that we know that minus 1 over 0 is the least number, we might as well define it as minus infinity. And we may as well define 0 over 0 as the number nullity. Now I stress this is not the sequence that you would teach anybody transreal arithmetic. This is a sequence I enjoy. It's a logically valid sequence. The way you actually teach it to people will depend a lot on child development, on how you go about teaching mathematics. So my conclusion, symbols, logic, and sets are an inadequate foundation for mathematics and transmathematics. Trans-symbols, trans-logic, and trans-sets are an adequate foundation for mathematics and transmathematics. And trans-symbols, trans-logics, and trans-sets are bijectively and potentially homeomorphically interchangeable. And again, I want the homeomorphisms so that I can handle knowledge that's not expressible in text. And everything is transcomputable and tetrachotomous. I should add that I've changed the idea of definition. So in mathematics, things can be defined or undefined, and now being undefined is not a possibility. Everything is a classification somewhere in a transset. So the things that were undefined, I would usually associate with the background. So I'm just classifying, everything exists in the universe, I'm just classifying where it falls in the transets that I'm discussing at that particular moment. So mathematics is totalized to transmathematics by translogics, transets, and the axiom of total comprehension. Transset classification defines everything, as I just said. All measurements are tetrachotomous. Transmathematics succeeds everywhere because the axiom of total comprehension can be used anywhere. And it's immensely liberating. Until now, if you wanted to develop some new mathematics, you had to develop axioms, you had to make them consistent, you had to make them describe whatever system it was you had. Now you can be sloppy. You can over-specify, you can have contradictions, you can have gaps, and still take the interior, still take the set, and then build up from that partial solution to a total solution. So it's giving you the freedom to go beyond the bounds of logic in your construction of mathematics, which I guess is why it's kind of hard to understand what I'm doing, because for these many years I've been going beyond the bounds of logic, and I've now been able to formalize how I'm doing that. So the question is, why was I able to take these 12 steps when mathematicians hadn't done that? And the answer is that 12 steps is a lot of steps to take. But I wasn't doing it axiomatically. If I was doing it axiomatically, I would have to make 12 consistent steps. I was working algorithmically. I was changing the notions of addition, subtraction, and so on. And algorithms don't have to be consistent. Algorithms can have gaps in them. And so I was working with a partial system that I could improve, and by a method of directed evolution, I could arrive at a solution. Much, much harder for mathematicians working with axiomatic systems to magically put together a system of 12 axioms that does a job. And that's an interesting observation, that computer scientists have access to problem-solving methods that mathematicians currently do not exploit, which is probably a good enough place for me to stop. I should say that now that I've got to this point, I can start with a finite number of discrete symbols, because with the axiom of total comprehension, I can build up any object I want. So I'm now back in the position that I agree with mathematicians that a finite number of discrete symbols is enough to get the show on the road. And in my case, the show is transmathematics. The transmathematics succeeds everywhere in the sense that the axiom of total comprehension holds. But it's still the case that trans-science can still fail, because science has empirical content. It doesn't matter how wonderful your mathematical theories are, they might just be wrong. The universe might not work that way. So I'm still in the position that I was with this first book, that there is the ability to divide by zero removes the guarantee of failure from science. But I'm in the stronger position on mathematics, which is that transmathematics guarantees success. You're always going to be able to write down a solution to any mathematical question. It might or might not be a satisfying answer. Right, I shall stop.
So why should we believe that all of this is consistent?
It doesn't have to be consistent. It has to classify against all the possible outcomes of gap, true, false, contradiction. Now, the reason why you might believe it is consistent is where Walter first got involved on paraconsistent logics. So Walter arithmetized paraconsistent logics using transreal arithmetic, and transreal arithmetic is known to be consistent. There is a machine proof of that. There are now half a dozen proofs. So if we take the route of building up transreal arithmetic from, sorry, was building up translogic from transreal arithmetic, then we inherit the properties that it is consistent. I'm struggling to turn off screen sharing. Have I turned off the screen sharing? Can you see my face in the big?
No.
No, you still see the screen.
So there.
Okay.
Still a stamp.
There's still a stamp. I'm struggling. Stop share. That's what I want.
Yeah.
Yay. Phew.
But the whole thing could be as wrong as what Frege and Cantor did.
It could be useless.
No, but wrong.
Okay. Challenge to you, Jan. What would count as this theory being wrong?
You derive 0 equals 1.
Yes, trivial. You might be saying that this theory must have some logical error.
Right. Okay, so I've realized what would count against it. So of course I can have contradictions. They occur in the boundary of a transset. If I took the interior of an antinomy, that's a set, if that nonetheless had an antinomy inside it, then I'm wrong.
Okay, so why is that not happening?
That's a good question.
Is it? Okay, if it's a good question, what's the answer?
I think the answer is I don't know.
What's that theory? When you are teaching students, you have a pictorial image that has two possibilities, inside, outside.
Yeah.
A error comes when something is in the boundary.
Yeah.
But boundary is not a error anymore, it's just a possibility of the error. So what maybe the error would be if you can transform what is outside and inside, outside. But in this case, the boundary will be the case. So what I'm trying to talk is false, true, contradictory. I think errors. I think that things exist if you have two possibilities only. But if you have outside, inside, boundary,
and
every
background
possibility
has a place. So none of them is an error, and that's my thinking, that it's a classification of logic. So I found it very hard to answer Jan's question, what would count as evidence against this theory? But I, in that moment, had the insight that if you take the interior of a transset, it's supposed to be a set, if it is nonetheless contradictory, then my system has failed.
You are saying that every sentence has a definite position is such
Yeah. And furthermore, my claim is if you take the interior is not contradictory. It doesn't have an antinomy. So if you could construct a transet, take its interior, and the interior did have an antinomy, then I'm wrong.
So there is a criterion.
There's a criterion.
Now the question is how to understand that this criterion is met.
Yeah.
So is there anything else than formalizing this in classical mathematics and proving the thing sound or consistent?
Proving soundness is challenging because we've got to deal with contradictions. So
yeah, you can of course we can formalize everything in two-value logic.
Yeah.
I just wonder what kind of work needs to be done in order to obtain trust in the consistency of this stuff.
Okay, so the work I'm planning to do is to develop the logic further than I've done in the book. So to write it down so you know what the operators are, you know what the inductive steps are, to specify the transet operators of union, intersection, difference, and so on, so that we have a very clear claim about what translogic is, what transet theory is. I haven't at the moment moved as far as...
Only if that's done, of course, consistency starts to matter.
Yeah, exactly.
Once all details have been laid down,
the
consistency question emerges. And it can be just traced or false, or why don't you add 0 equals 1? Answer, because then we would derive more than is out. Is that the case? Right.
Okay.
Thanks.
Right, so thank you everybody for attending Transmathematica 2025, the 6th International Conference on Total Systems. Do submit papers to the Transmathematical Journal so that you'll get a free place to present at the next Transmathematica Conference. Thank you everybody, goodbye.